Software Engineering Radio, episode 130, called Visualization with Michele Lanza.
This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio brings you relevant and detailed discussions and interviews on software engineering topics every 10 days. Thanks to our audience and the partners listed on our website for support. Welcome listeners to a new episode of Software Engineering Radio. This is another episode we are recording here at JAU 2008, same procedure as every year. Today we're talking about software visualizations, and you have to think about this like an audiobook, right? The fact that you can't see things in the podcast helps you because you can imagine things to be, really great. To do this discussion today, we have a guest, Michele Lanza.
Hello.
Why don't you introduce yourself to our listeners so they know who they're listening to?
Okay, so my name is Michele Lanza. I'm Italian. I'm an assistant professor currently at the University of Lugano, that's in southern Switzerland. And before that, I did a PhD in Bern, that's in the German-speaking part of Switzerland. Interesting to know, I'm Italian. Really important.
I wouldn't have guessed. I mean, you speak absolutely perfect German, so...
Oh, yeah, thanks. But I've been like 25 years in Switzerland.
Okay.
Well, not everybody's perfect.
I don't know what that means in this context, but... Okay, so we want to talk about software visualization today. And before we get into the details also of the tools you built, why don't you give us an outline of what software visualization is and why it is important?
Okay, so software visualization is basically the depiction of software constructs, and the main purpose is to understand software.
Mm-hmm.
So think of this as in every software system, basically you have entities and relationships. So for example, you have classes, methods, attributes, that's the entities, and you have relationships like inheritance, invocation, attribute access, and so on. So lots of visualization tools are based on a graph notion, where basically the entities are nodes in the graph and the relationships are the edges in the graph. And you basically depict a software system. You take any software system and you can depict it as a graph, basically.
And we'll talk about later about the information you can gain from looking at it. But I think it's important to at least briefly talk about the difference between software visualization and the classical modeling. People might think about UML kinds of things once they hear about visualization. Is that what you're talking about, or is it different, and if so, how?
Well, an important thing to say is that visualization is not UML. Okay, UML is a visual language to describe the design of a system. And the good thing, because UML bashing is very easy, the good thing about UML is that it is a universal language. You can give a UML diagram to a developer in Brazil or in Japan, and that person will understand it nonetheless. Okay. Now, visualization works at a different level. There, the point is to depict software in a way which communicates me, thinks about the system. Plus, UML does not really scale up. If you have a class diagram of a system of 1,000 classes, you will not really understand anything because it's just too much information. Good visualizations are basically abstracting away all the complexity into simple pictures that allow for interpreting the pictures.
So is it fair to say that if you want to visualize something, you should first think about what you want to communicate and then think about two things. One is the suitable abstractions of things that, what needs to be shown in the diagram, what's the abstraction, what's the level of detail maybe, and the other thing is how to graphically render it so it's easily accessible to the viewer.
So basically I started doing all this around 10 years ago when I was a master's student at the University of Bern. And we had this project together with a couple of European companies, one of which was this Northern telecommunications company. So they had very large systems that they needed to understand. So one day they basically invited us to go there and tell them something about their system, because it was so complex that they had kind of lost track about it. So the point there is that you cannot go there and use some massive tools to do all that because you don't have the time. So you just start with very simple approaches. So the one I kind of invented, although I don't think that there's any invention there, was basically to provide this graph-based notion of visualization I talked before, but enrich it with information about the entities and the relationships. So this led to the concept of a polymetric view, which is basically a graph visualization enriched with software metrics. So just free your mind, the rest will follow. Imagine this. You basically have a square representing an entity, and now you use metrics on top of that, representing the width, the height of the square, and also the color of the square.
Yeah.
And if you do that, you get this enriched visualization that can tell you actually things about the system. So instantly you will see the large things, you will see the small things, you will see the dark things.
Yeah.
And that's the whole point. It's a very simple idea, but actually it works.
You talked about, well, if I say you talked about, then I should maybe add that I've just seen your talk at JAU. So in your talk, you talked about a couple of primitive graphical elements or relationships between things that stand out and that make us easily comprehend something. Can you elaborate on those a little bit? Because, I mean, those are the basis for visualization then.
So basically, let's put it like this. I read a couple of books on how the brain works. There's a couple of wonderful books. So just book pointers. One called Stephen Few, Show Me the Numbers, and the other one by Steven Pinker, which is called How the Mind Works. So there basically researchers assessed that we see with our brain at 3 different levels. So we have this iconic memory, we have short-term memory, we have long-term memory. Now, long-term memory, that's not the topic. This is really remembering.
Yeah.
Iconic memory works like a buffer. You see something, and iconic memory retains what you see for less than 1 second before it passes it on to short-term memory. Short-term memory is the one which has limited capacity. Now, iconic memory works based on a couple of fundamental principles, and there's not that many. So these are called pre-attentive attributes. So for example, if you have 2 lines and one is longer, to see that the one line is longer will not require you to consciously process that. Your iconic memory will do that automatically for you. So the number of pre-attentive attributes is limited. So for example, you have the line length, the line width, the size of something, the color of something, and so on. And those primitives are actually the ones that you can use for depicting anything, including software.
So that would mean that if you talk about metrics in your polymetric views, that you take a certain characteristic of an entity. For example, it's lines of code in a method or the number of methods in a class, and then you assign that to the degree of length, color, width, and then this allows the iconic memory to easily spot the outliers, basically.
Exactly.
Yeah.
That's the point.
Yeah. So that's also, I guess, the whole idea of visualization, to easily spot things that are kind of strange.
Yeah. And the major point there is that to do that without reading the code. So you just look at the system and no source code is displayed.
Right.
Although, to be honest, at one moment in time, you must start reading the code, because software is not about pictures, it's about source code.
Yeah.
But before you actually go down to the level of source code, you can spend a lot of time saving time at the level above, where you just look at the large system with these constructs.
So based on that, you have built a couple of tools.
Yeah.
So why don't you give us a little bit of an introduction to the kinds of tools you built, the 2D ones, the 3D ones, and then we can talk about what they're useful for and how they can be used.
I started basically building tools with a tool called CodeCrawler. It was a very simple tool which implemented the concept of polymetric views. And with that, you could actually reverse engineer and understand large-scale systems. And that's what I did actually during the course of my PhD. Then CodeCrawler actually got extended into visualizing the internal structure of classes using class blueprints. I also extended it to visualize the evolution of systems with, again, very simple concepts, one of which is called the evolution matrix. This basically was my whole PhD. Then when I founded basically my research group at the University of Lugano, we started building a massive range of tools. So we started with 2D reverse architecting tool, where basically you look at the system from above. This is the work of Mircea Lungu. And you can basically tear the system apart in terms of its packages and get an understanding of its architecture.
Mm-hmm.
At the same time, there was another PhD student called Marco D'Ambros. He started by extending CodeCrawler to visualize bug information.
Mm-hmm.
So you could actually see which entities in the system were affected by which and how many bugs. And then you could actually reason about that. At one moment, basically, we also started doing Java tools, because so far all the tools I've mentioned actually have been written in Smalltalk.
And also for Smalltalk programs, I guess.
No, actually they worked also for non-Smalltalk programs, like C++ or Java, because we had this language-independent meta model that we can use.
Mm-hmm.
At the moment, we started to write Java tools, basically Eclipse plugins, and although some of them are actually fairly successful, like one called X-Ray, written by a student called Jacopo Malnati, which these tools, by the way, are all free and open.
Right. And we'll put the links to them into the show notes.
Okay. We started recognizing that there was no use in trying to compete for the real estate on the screen of an IDE like Eclipse, because programmers, when they program, what they want to see most of all is actually the code itself.
Right. Yeah.
That's why they blow up basically the code pane, the text editor pane, and minimize all the rest. So a visualization tool doesn't have a great chance there. So we basically tried then to go the completely opposite way by trying to create an immersive experience. So we've started writing a tool, and this is the work of a PhD student called Richard Dettel, where we visualize software systems as three-dimensional cities into which you can immerse yourself. So we used the metaphor of a city. We played around with a lot of metaphors, but in the end we settled on the metaphor of a city because of two reasons. First one is that cities are a known concept.
Yeah.
People live in cities or have been to cities, hopefully, so they know what it's all about. Yeah. Second, I don't think that software visualization is about oversimplifying the complexity of software systems. So a metaphor like a city works really well because a city is a complex construct that needs to be explored progressively, and we will actually want to imply the same on software systems, that you need to slowly immerse yourself into that and start to get a feeling of what the system is all about.
So that means, if I try to describe this a little bit for our listeners, and again, I also encourage you guys to actually visit the show notes and look at the slides, because there are really nice visualizations in the slides, which we probably cannot do justice through the audio communication here. But if he talks about code cities, then this really means that you literally have building-like structures with a certain width and a certain height and maybe a certain color, where height, width, and color, as you mentioned before, represent some of those metrics. Yeah. And you really get like certain, you talked about parking lots, skyscrapers, antennas, right? Things that are flat and big, that are massive, or that are high and tall. So it's really, really very useful.
Yeah, the other thing is also, apart from looking at the slides, these are basically pictures. You should really download the tools. Yeah. Because the point is that in such cities, you can really walk around. You can touch things. You can modify things. You can tag them, for example. You can colorize them, and so on. And this is the point. I don't think software visualization is about creating nice pictures about system, because these pictures won't tell you enough. It's really about this navigation experience, that you can immerse yourself into those visualizations.
Yeah. So, based on those renderings, people might ask themselves, so what do I do with those? What's the point? What kind of applications can we have, or what can we actually achieve with those city diagrams or city maps or whatever? And I guess there are three applications that you talked about, and why don't we look at each of them briefly? So the first one is program comprehension.
Yeah, basically the point there is that you have a large system in front of you that you don't know about, and you must get some kind of bearing of the system. You must understand what the system is all about. Now, what you can do in such a case is either you can start reading the code, but this is not really realistic, because if the system is really large, you will spend a lot of time, and this doesn't necessarily imply that you will actually understand the system. Right. So for this, we use these city-like visualizations to give an instantaneous feeling for how the system looks like. And that's also actually something that I can hardly talk about just orally. But if you visualize different systems, you will start to recognize that they are really diverse in nature. So some systems have more a good distribution of functionality, so there are no skyscrapers. Okay, so all the classes have reduced amounts of functionality. The system is really well structured, while in other systems you have these monster classes where everything is concentrated, and you instantly actually see that. Plus, another thing that we have also seen is that there is something going on with languages. So we visualize systems in Java, Smalltalk, and C++, and you actually see that there's different typologies of cities depending on the language. But this is leading to a completely different topic that is not the subject here.
Well, but at least it suggests different cultures of how the OO paradigm is understood, right?
Oh, yes, absolutely.
So that's, I guess, the message there.
Plus, I guess that the language like C++ can hardly be called object-oriented, right?
Yeah, I mean, why did I know that you would say this as a Smalltalk guy? Now, if I imagine that you have those snapshots of the system displayed as a city, then of course the next question is, can you have movies in the sense that you show the evolution of a system over time?
Oh, absolutely. That's one of the more obvious things that you actually do. So we actually did that on a couple of systems where we basically took snapshots of the system, like a good number, okay? And then for each of the snapshot, you create one three-dimensional depiction. Then you can concatenate all those pictures and create the movie of the evolution of a system. And we did this with a couple of systems. And the good thing there is that while, of course, a movie does not allow you to interact with the system, the whole movie gives you actually a story about the system. You clearly see how the system has evolved over time, when there have been major restructurings in the systems. Plus, of course, you can always add additional information on top of that. So, for example, you could use colors to denote who actually wrote which parts of the system.
Yeah, or when.
And then you could actually really see who is responsible for which changes in the system.
And I mean, again, it's hard to do it audio only, but if you look at the slides, you will really be, I mean, yeah, you said it's not about pretty pictures, but it really helps you to get an overview, and I guess that's the point. Before we look at the third application, I really want to reiterate this thing that I think, well, that's my personal opinion. My background here is that I work a lot with models, and over time, I've really come to the conclusion that graphical modeling in many cases doesn't really work. So I really like to do graphical DSLs for modeling and then use visualization to give you the overview, and then maybe a drill down capacity so you can double click a bubble and you back to the text. So what's your opinion there? I mean, do you think interactive graphical construction of systems, graphical programming, is that a dead end?
It is a dead end in the way that it was performed in the last 20 years. So some people have done amazing visual programming languages, but I think what they got wrong, but that's my personal opinion, okay?
Of course, that's why I'm asking you.
Is that they tried also to use the visual programming language at the sub-method level. Mm-hmm. So actually you were writing, for example, imagine that you have to write a bubble sort algorithm. So you would actually compose the bubble sort algorithm graphically.
Yeah.
And I think that this just doesn't work, because in this case, the description of what you want to do is more complex than the things that you're actually describing.
Yeah.
And this doesn't make sense. So I think that below method body or below functional units in the system, you must actually write source code. But above it, visualization there makes a lot of sense, and also visual programming.
Yeah. So the way I like to distinguish things is, as soon as you have the entities and their relationships, or a kind of signal flow, or a timeline that advances and you want to show events on the timeline, there a graphical description is really useful, because it really gives you the essential information, which is temporal relationship or the relationship between entities. But as soon as you don't have one of these criteria, you're screwed graphically.
Yes, absolutely.
Yeah.
I mean, visualization is about breaking down complexity. That's the whole point. If a visualization does not succeed in doing that, then it's useless.
Right. Application number 3 is, if I paraphrase it, smell detection.
Yes.
Right? So what you do is you basically implement certain metrics that detect smells and then highlight those.
Yeah, so 2 years ago I wrote a book together with Radu Marinescu from Technical University of Timișoara. where the book basically is a merge of two PhDs. My PhD, which was in visualization, and Radu's PhD, which was in metrics. So Radu, during his PhD, developed this concept called detection strategy. A detection strategy is a formalized design heuristic. So imagine that you have a design heuristic like a God class. Okay, a God class is a problem. You go and read.
What is a God class? Just to be.
A God class basically is a class that tends to centralize intelligence of the system. So because of that, it starts to misuse the classes around it as mere data holders, while it tries to do everything itself. And what I've seen also by observing the evolution of God classes is that these things have this cancer-like connotation, where over time they start to suck in functionality out of the other classes. So a God class can be seen like this. If you are a programmer and you don't really know where to place information in a system, then you go and place it in God class. And because of that, they have this abnormous growth. Now, detection strategies are metrics-based conditions to detect fragments of the system that exhibit design problems. So we have, for example, defined a detection strategy to detect God classes based on metrics. And what you do there is, if you run such a detection strategy, it's like a filter. It will take the 2,000 classes in your system and it will spit out the 50 classes in the system that have this particular design problem. Now, one problem there is always to inspect the results. Because if you get back a list of 50 classes, well, what would you do? You would start to go through one class after the other. So what we did there is, by taking inspiration from disease maps and also from CAT scans, where you have, for example, you have a CAT scan of a brain, the inactive parts are grayed out, and the parts that are active have very live colors. So we do the same. We represent the systems as 3D cities, all grayed out, and where there is a design problem, we just use live colors. And this actually gives you an instantaneous feeling for which parts of the system you should look at, because these parts exhibit design problems.
So in some sense, it's as you say, a visualization of metrics and making the result of a metric detection thing visual. To
a certain extent, this goes, and that's also where one of my research tracks will lead into the future. It goes towards augmented reality. So you have this fully immersive experience around you, but computer graphics allows you to actually augment it by add additional information on top of that. You can imagine it a little bit as walking through a city, and then there is this pointer in your field of view that tells you that there is a good restaurant.
Have you thought about integrating your system or advertising your visualizations towards those typical, software tomography or clockwork, whatever they're called, those static analysis tools? Because they also have all those metrics in them, but they don't really display them in a very, very accessible way. Have you thought about integrating those or making them use your approach or whatever?
Well, let's put it like this. At least a couple of those that you mentioned actually took heavy inspiration from our work.
Okay.
That's for sure, at least. Then the other thing is, the problem there is that visualizations do not really work just as pictures, as I said before. So you need to actually use the tools.
Right.
And this usage of the tool is not...
Let me try, because I think I know what you're saying, and that is, you should use the ability of the tool to interact with the model or the picture, as opposed to having this paper metaphor where you just display something.
Exactly. If you look at certain tools that actually do code quality analysis, what you do there is basically you press a button and it generates you a report about the problems in the system. And then the manager is happy, because he can give that report to some guy, and that guy will go and fix it up, hopefully. Now, with visualization, this doesn't really work. You must really dive into the system. And this interactive notion, to some people, looks not scientific enough, or not empirical enough, or not stable enough.
But it's really interesting because all the current, again, going back to UML, all the current UML tools still have this paper metaphor. A diagram is a passive thing that sits on the screen. You can print it one-to-one. There is no, for example, what I would like to have as kind of a minimum is I have a class in UML and then it has a bunch of associations, but they kind of end in infinity, and then you double-click the associations and the classes that are at the other end of the association like pop up and come into the center. An interactive, exploration of the diagram. So I think this disease of having diagrams as something that can be printed with this paper metaphor is a big problem, and that's what you basically just talked about, right?
Yeah.
So all the stuff we talked about until now was basically the description, or the visualization, I should say, of structure. Can you also visualize behavior, and what would that mean?
So we have done some work in visualizing the dynamic behavior, runtime behavior of systems. One of the problems there is the data. You have basically a complete data overkill. So if you trace a system, even if only for a couple of seconds, you end up having tens of thousands or hundreds of thousands of events. And while, of course, these events are all relevant because otherwise the system wouldn't work, a lot of them is actually noise, because in the end, what you really want to do is to understand how the system is behaving while it is running, and or if there is a problem in the behavior. So in this context, we have done basically two kinds of works. The first one is to try to visualize in 3D again objects and message sends as they happen. This worked actually, but led to a lot of overplotting problems. The other one is to take the static structure of the system in 3D and superimpose on top of that the dynamic behavior. This kind of works, but it's ongoing research.
It's not clear yet whether it's going to be extremely useful or not.
No.
Okay.
And again, I mean, when it comes to research, what I should mention is that what researchers usually present is like a 1 out of 10 thing. So they try 10 different things and 9 out of 10 don't work. And then one works. So while sometimes it may look really simplistic, there's a lot of work behind it. And a lot of, in a certain way, unnecessary work.
Yeah, if you only knew before.
Yeah.
Last question. So I guess you're generally involved in the visualization community.
Oh, yeah.
And that is a different community from the modeling community. I personally think that the modeling community could learn a lot from the visualization community, because again, models are just data, and comprehending those data is a big challenge in bigger models. So is there any attempt at kind of, having those two communities work together? Are there any venues? How, is there a workshop that says, I don't know, using visualization techniques for just UML models? I don't think UML is very useful, but you get the point. Is there any such thing, or do you think it's worth trying to have something like that?
Well, sad news is that there is nothing. Okay. So I can also, on a side note, I can say that software visualization doesn't have an easy life, at least in academia. Because if you go to many software engineering conferences, what these people want is empirical results on things. So you have to prove to them that whatever you do is better than something that somebody else has done before. And in the case of visualization, this is not so easy, because how can you evaluate whether a visualization really works or not? So one way would be to use, for example, human guinea pigs, right? So you take a couple of people, some of them you give them the visualization tool, and the others not. Well, the problem is that you can always tweak the questions in a way to make your tool look good. Okay? And I don't think that this is scientifically honest. Then the other thing is also that, for me, it's funny to observe during the last 10 years that whenever I show visualizations, the academic part of computer science is not convinced, while the developer community actually loves it. So there is some deeper truth behind that, but I still have to discover that. Now, with respect to the question, is it worth to look at modeling in the context of visualization and vice versa? I definitely think so. But if you look at conferences like Models, that's like the conference on modeling.
Right, yeah.
There's nothing on visualization.
Mm-hmm.
It's really, really hard.
So I guess there is something we need to do next year, either at Models or at Oopslar or something, and try to actually, or maybe even at EclipseCon. There's a couple of visualization projects on Eclipse. Maybe to try to submit a workshop and get this going, because again, I work a lot with textual languages and I need visualization, and all the quick hacks I built aren't really good. So I think that would be really interesting.
Well, one thing I can say is that if any of the listener is intending to visualize something, maybe based on the inspirations gotten from looking at the slides, is that whatever you do, never ever forget that visualization works based on a couple of very simple principles, the one that we talked before, the pre-attentive attributes.
Yeah.
So any visualization must take that into account. So it's not about generating beautiful stuff, okay? It's about generating meaningful things that can actually help you.
Right. Is there anything else you want to say, want to leave with our listeners before we shut this episode down?
Well, one thing I have to say is that although conceptually a lot of this comes out of my brain, I should also mention that I wouldn't be anything without my PhD students.
Yeah.
Okay, so I should mention them again. That's Roman Rob, Mircea Lungu, Marco Dambros, Ricky Vettel, and Lile Hattori.
Okay.
These guys right now are my vehicle
workforce
to express whatever I think, although they are much better than I am.
Okay, Michele, thank you very much for being on the show.
Thanks.
Thanks for downloading and listening to Software Engineering Radio. Software Engineering Radio is an educational program brought to you by Hillside Europe. If you want more information about the podcast and all the other episodes, visit our website at se-radio.net. If you want to support us, you can donate to the SE Radio team via the website, or you can advertise for SE Radio, for example by clicking on the Dig, Reddit, Delicious and Slashdot buttons. To contact the team, please send email to team@se-radio.net, or if it is specific to an episode, please use the comments facility on the website so other people can react to your comments. This episode of SE Radio, as well as all other episodes, are licensed under a Creative Commons 2.5 license. Please see the website for details. Thanks to Charlie Crow and the PodSafe Music Network for the music used in this show. The song is called Vegas Hard Rock Shuffle.